Hey everyone, today we're going to be talking about the chain rule. Now as always, before we get into the video, I just want to let you guys know that we'll be using some concepts mentioned earlier in the series. So if you haven't checked that out, be sure to take a look. Alright, so before we get into the chain rule, we first need to address what a composite function is. And a composite function is just a function whose input is another function. So that just means that it's a function within a function. Let's look at an example of this. Let's say we have f of x is equal to 2 times x. And let's say we have another function, g of u is equal to u squared, where our input here is u. So if we wanted to know something like what is g of f of x, then what we're saying is we have our function g and our input is f of x. So this would look like our function, which is our input squared. So we'll have f of x squared, and it's going to look like this. And as we know, f of x is equal to 2x, so we'll have 2x squared, and in the end, this is equal to 4x squared. And we are looking for the derivative of a function like this, a composite function. And finding the derivative of a function like this, where it's only just a polynomial, is not too hard. But what if we were to mix two different types of functions, like a polynomial and a trigonometric function? How would we go about this? Well, let's see what we can do by writing out our derivative equation. So, our derivative equation says that dy over dx is equal to the limit as h goes to 0 of f of x plus h minus f of x all divided by h. But this is when y is equal to f of x. And another way to write our derivative equation is df over dx. And this notation doesn't change anything because we still have the change in our output, in this case, f divided by our change in input, in this case, x. And this is okay because, as we see here, y is equal to f of x. So these two are saying the same thing. But what if our function didn't equal y and it equaled some other letter, like g of x? Well, if we had that, then we can say that g of x is equal to f of x, and the derivative of this function could be written as dg over dx. And this is not changing anything because in this case, our function is equal to g of x or f of x. So dg over dx is equal to df over dx. And if our function happened to have an input other than x, so let's say g of f of x, where f of x is our input, then the derivative of g with respect to our input f of x would look like dg over df. This is the same idea as if we were to do another letter like g of r or g of u. The only difference is our input happens to be another function. So, using this knowledge, we can tackle our derivative problem. Let's say we have two functions. We'll have f of x and g of u. Now, it doesn't really matter what these equations are equal to, as long as we can make a composite function out of them. If you want, you can follow along at home and set these functions equal to something, and that's okay too. So, let's say that g of f of x is equal to some new function, which we'll call j of x. So j of x is equal to g of f of x. Well, we can write the derivative of j of x as dj over dx, and that is equal to the limit as h goes to 0 of j of x plus h minus j of x, all divided by h. Now, we can substitute our functions, so we'll have the limit as h goes to 0 of g of f of x plus h minus g of f of x all divided by h. Now, as you can see here, we can't really work with this form, and we need a way out of it, and we have to work around it. Our function g has an input f of x, and we know that the derivative function normally has our output section in the numerator and our input section in the denominator. So we need some form of f of x plus h minus f of x to be in our denominator. So what we can do is we can divide both sides by f of x plus h minus f of x. So it will look like dj over dx times 1 over f of x plus h minus f of x, and this is equal to the limit as h goes to 0 of g of f of x plus h minus g of f of x divided by h, and then we'll have this times 1 over f of x plus h minus f of x. And we can see here that we haven't actually changed anything about our original derivative equation because whatever we did to the left side, we also did to the right side. So what we did here is okay. Now, on the right side, let's rearrange our denominators so that f of x plus h minus f of x is in the denominator of our g function. And this is okay just because of the property of multiplying by, with fractions. So we'll have dj, or actually I'll just set this equal to it because we're saying the same thing here. So we'll have this equal to the limit as h goes to 0 of g of f of x plus h minus g of f of x divided by f of x plus h minus f of x, and this is times 1 over h. So we can see that we haven't actually changed anything. So what we need to do is solve for the derivative of j of x. So let's bring our f of x plus h minus f of x from the left side over to the right side. So what we'll have is dj over dx is equal to the limit as h goes to 0 of g of f of x plus h minus g of f of x divided by f of x plus h minus f of x, and this is times f of x plus h minus f of x, all divided by h. So what we could do here is cancel our f of x plus h minus f of x's, but we would just go back to the same spot and we would just have gone in a circle. But what we see here is that we have our output section in the numerator here and our input section here. And we also have the same thing over here. Our output section's up here and our input section's down here. And that means that we can just write this as derivatives. So we'll have dj over dx is equal to the limit as h goes to 0 of, well, the derivative of g of f of x we wrote before as dg over df. We're saying that it's the change in our output, g of f of x, divided by the change in our input, which is f of x. And this is multiplied by something more familiar, which is just df over dx. Now, if we wanted to, we could technically say that we're canceling our df's and we'll be left with dg over dx. And this means that we're taking the derivative of g with respect to x, but x is not our input. X is the input of the input of g. However, there is actually another way to write derivatives. The derivative say of f of x, if we have f of x here, we can say that the derivative of this is equal to df over dx, but another way to write this is by saying df over dx is equal to f prime of x. And this is saying that it's the first derivative. Now, we can get into first and second derivatives, but that's going to be in a future video. For now, what we need to know is that this means the same thing. And using this knowledge, we can say that dg over dx or dg over df times df over dx is equal to g prime of our input f of x times the derivative of x, which is f prime of x. And this is what the chain rule is. This right here is what we were looking for. And this is a very important rule, because if we have any sort of composite function, the derivative of that function is what we call the derivative of the outer function, with our input remaining the same, multiplied by the derivative of the input. And this is a very important derivative formula, which we'll be using for many other proofs as well. Let's try and use our chain rule formula and revisit our first question. So if we have two functions, f of x is equal to 2x, f of x is equal to 2x and g of u is equal to u squared. And we create a composite function out of this by saying j of x is equal to g of f of x. Then, as we know from before, this is equal to 4x squared. And if we were to take the derivative of this equation, so j prime of x, this would be equal to our power multiplied by our coefficient multiplied by our variable. If you don't remember this, we went over this at the end of the first video in this series. So if this is feeling like something you're not sure about, make sure to check that out. But we'll have 8 times x. And that's the derivative of j of x. But let's see if we can also use our chain rule formula to get the same answer. So we'll have j prime of x is equal to the derivative of the outer function, which is, in this case, 2 times our input, 2x. So 2 times 2x, and then multiplied by the derivative of our inner function. And in this case, the derivative of the inner is 2. And we're actually still left with 8x. So we know that by using either the chain rule, or in this case, our quadratic rule, we don't really have a name for it right now, but just using our regular derivative formula, we get the same answer. So our chain rule works. So let's try this with a more complicated example. Let's say we have a function f of x is equal to x squared, and another function g of u is equal to the sine of u. Now, if we create a composite function out of this, So j of x is equal to g of f of x. We will have j of x as the sine of our input, which is x squared. So we can see here that this composite function has both a trigonometric and a polynomial function. So we can't use either our regular derivative formula or our sine derivative formula, which we had from the last video. And we have to actually use our chain rule formula. So we'll have j prime of x is equal to the derivative of our outer function, which is the cosine of our input, in this case x squared, multiplied by the derivative of our input, which we know is 2x. So I'll just write this a little nicely. J prime of x is equal to 2x cosine of x squared. And we wouldn't be able to get this using our basic derivative formula, or at least very easily. So the chain rule bypasses any sort of problems we might have, and it really helps with calculus problems. Thanks for watching this video. In the background here, I have what would happen if you were to switch the order of your functions in the composite function. So j of x is equal to f of g of x, which is equal to the sine squared of x. And that would mean that j prime of x is equal to 2 sine of x cosine of x. So make sure when you're using this chain rule that you know which derivative and which function you're actually looking at, because you might end up switching the order and getting a different answer. I hope that this video was helpful and that you understand more where the chain rule actually comes from. If you want me to go over something specific, just let me know in the comments and I'll do my best to help. And until then, I'll see you in the next video.